some of these terms get thrown around and maybe they're not exactly the same, you know, simulation and a digital twin and virtual commissioning. So if you have a CAD model in, say, the Siemens NX CAD software, NX, or could SolidWorks or whatever, in many of these tools, and especially in the Siemens tools, NX, you have a CAD model of a machine, and you can do a lot with that as far as finite element analysis and testing and so on. But you can also, with some add-on modules, you can bring that machine to life. So a static 3D model can be made to move in the CAD software so that it is going to, you're actually going to really see how the machine will run. And you can load material into the machine and see how the machine reacts to the material, how it's making the parts and so on. So a visual representation of how the machine will really run as opposed to a static 3D model. So CAD software was able to do that for a long time and is getting better and better and more advanced and much better fidelity in how it's able to bring this 3D model to life. Where the virtual commissioning in particular comes in is the mechanical engineer can drive those simulations internally. He can just create his own little sequence chart, you know, do this, and then do this. He can write a little script in the software, in the CAD software, or create a timing chart to do that. Virtual commissioning is where we say, okay, instead of the mechanical engineer dreaming up, this is how the machine's going to run, we bring in signals from the automation, and they can be coming from a real PLC, or the best use case is what we refer to as software in the loop. We are bringing in the signals, the I/O signals from a virtual PLC. We can suck those into the CAD software and then use those tags and the behavior of those variables, on, off, or integer, real, whatever. We can use the behavior of that data to trigger the simulations or the emulations that you see in the machine. So that therefore, when you run the simulation, you have on one side mechanical software showing how the machine will run, and on the other side automation code that's actually running it. Turn on the machine, move the part down the conveyor. When it hits a sensor, stop, extend the arm, so that the PLC thinks it's communicating to a real system. And so it's a total game changer in a sense of really being able to validate what the machine is going to do, because it's not just the mechanical engineer, you know, going through a sequence. It's the automation engineer with his full code behind it. And then, of course, so long story short, it's the bringing together of the automation world to the mechanical world, where the automation world is driving the simulations that you see. And all of a sudden now the automation person has a virtual machine that he can then test his code against. In the past, he was normally at the end of the line. We all know, we're all automation guys here. We were the ones who get dumped on when mechanical guys out there, sorry to say it, but between changes and maybe you go on vacation or whatever, you know, we get them, our time that we thought that we would be able to debug in the machine is usually far less than what we were told we would get. But of course, the ship date for the machine never changes. So we get squeezed. So the ability to do all of that code testing, and as we know, any of your coders out there know the 80-20 rule, right? That last 20% is all of the what if scenarios, and have you accommodated for this? Those are the ones that will kill you on a real machine, on real commissioning, when you were not able to, like, all of a sudden the machine shows up, and it's just slightly different than what you thought. The parts are slightly different. The position of sensors are not where you thought they would be. If you're able to kind of rewind the clock, go back in time, and now if I could test out all my code, and in particular, I love the error handling scenarios, because you could say for a lot of machines, you know what, the sequence of operations was pretty well known. We got that down. What kills you on the automation side is always the error handling and what if scenarios, where if this doesn't happen and this is happening at the same time, what's going to happen over here? That can be very difficult to visualize as you're an automation engineer without the real machine to really test it. And we used to joke, you know, when we would like, you know, download our code when we finally had the machine. It's like bombs away, right? You hit the download button for the first time and you hope that motor's going to go. You hope it's going to work and things. It's any of the automation guys know when you bring a machine to life, you do it very carefully, very slowly to make sure everything's working in the right direction. And of course, you still have to do that, you know, is to make sure that the stuff is wired correctly or the coupling is mounted the right way, that it's going to send the motor in the direction that you think it's going to go in. But nevertheless, long story short, having the ability to really debug and test your code ahead of time with all of your fault scenarios, those are the ones, because if there's a problem on the machine, we all know the operator is going to look at the panel, the operator panel, and if that alarm message is as clear and as precise as possible, and you have considered all of the what-if scenarios, then he should be able to, you know, fix the jam or just restart the machine or whatever he has to do, make it as simple as possible. And yeah, the sooner you can do it, the more you can fine-tune your code, iron out all of the bugs. So yeah, when you just get onto the real machine, then it's a whole set of other, it's going to be much smoother for sure. So again, long-winded answer to a simple question.
No,